All right, so let's go ahead and get started with tree support and lightning protection. These are the topics they decided to blend together. So we're going to talk about what the benefits of cable is, guying, bracing rods, and props. We'll talk about what the limitations are when you use those things, methods of providing supplemental support, the techniques and materials used in cabling and bracing, and then what's the arborist's responsibility when we use these things in trees, the benefits of lightning protection systems, the techniques and materials used in those. Why would we want to use these systems to begin with? There's probably some type of genetic defect, like a bifurcation where the tree splits off, which means you have sort of this codominant stem that becomes weaker over time. Now you could think about a Bradford pear as they grow in that secondary development, they begin to push on each other. So when they get to be about 12, 13 years of age, they just blow apart. And it's because of all those branches emanate so closely together. Same sort of thing happens even if there's only two. So this bifurcation, if it's a tight union like that, can create an environment where it will break just as from a product of growing. So by using cable systems, we can help reduce some of the strain in that area. Support may be needed for these defects and for trees that have already split, trees that have some decay close to the branch unions, multi-stem trees like maples, things like that have a bunch of upright leaders, or large branches that pose a threat. And like if a big branch was to fall and land on a carport or a building or your house, you might want to just be able to help that so that if it did break, it might swing to one side or the other, or it could even help to minimize the chance of that failure. Trees must be assessed carefully and tree conditions must be considered before installing. So, if you're trying to repair this defect, but you've got some major Ganoderma root rot going on at the base, well, you probably have bigger concerns than trying to install a cable. You might be thinking about removing the entire tree. There are standards that are written for this. There's the ISA's standards, or they're not really standards. They're going to be called best management practices, BMPs. But there is an ANSI standard for cabling, bracing, and guying. So it's best to read up on these things and sort of understand the wheres and hows and the exactness of it when it comes to either requesting or bid or fulfilling bids. So cabling itself does restrict the movement of the tree. So if you have this bifurcation and you're putting a cable in up high, when the wind blows, it can only go so far apart before that cable stops it from moving any further. So that's sort of what we want to have happen. We don't want it to pull apart, right? But there are some downsides to it because you can focus the forces where the cable is. So the cable needs to be far enough out where that becomes negligible. We'll see that as we progress here. Bracing rods are used to reduce the risk of two or more leaders spreading further apart or moving sideways in relation to each other. So we have this same sort of codominant crotch. We don't want it to do this either. This is more frequently what happens in a windstorm. You get torque, meaning this sort of circular movement, and you can also get it where it pulls apart. So bracing rods actually go down closer to the point of defect. So, and then guying, our third subject here, is the installation of a cable between the tree and some external anchor point. That external anchor point could be another tree. It could be a ground anchor that's screwed into the ground and cabled back to the tree that way. So again, the cable installation is going to limit the movement of limbs with weak connections. We can use it also to support heavy limbs by connecting two or more limbs together. And, if you have a really flat limb that comes off and one that comes off the trunk like this, we might be able to help share the load between these two. So it doesn't necessarily have to be a bifurcated trunk. It could just be large branches that help to support each other. And the multi-stem trees, we want those trees to kind of move together so that they don't twist apart from each other. It can also protect limbs and branches from heavy snow or winds. That's kind of a double-edged sword, but that's what we're going to go with. Cables should not be installed in a tree that does not have a structurally sound root system. So again, if you might have bigger issues than the cabling. Trees with decay should be considered for removal rather than cabling. So remember, decay slowly erodes away the structural integrity of the tree. So if you're installing a cable and there's already a lot of decay in there, the cable might just make it worse. And we'll see how that happens in a few slides. Before installing cables or braces in a tree, the tree should be properly pruned to remove the hazardous limbs and to reduce the weight. So if you can imagine a branch and it's full length branch and it's got lots of leaves out here, if I prune it, what's going to happen? It's going to sit back up like that. So if I install a cable system when it's like this, and then I go out and prune, my cable is going to go slack. So you want to take off the weight that you need to, or do all the pruning first, then install the cable system. If at all possible, it's even better to do it in the winter after leaf drop when even more weight's been taken off. So let's talk about some cabling hardware now. The cables are 7-strand common grade galvanized. This stuff's pretty easy to bend. You see the word malleable up there. That's usually like one of this word that usually shows up on the test somewhere, believe it or not. So malleable just means that you can manipulate it by hand. There's also 7-strand, but it's EHS. This is extra high strength. This stuff does not flex or bend by hand. You have to have something to help you out with that. This is where we would typically use a quick wrap around this extra high strength cable because we're not going to be able to bend it around a thimble, as we'll see. And then there's also aircraft cable, like the stuff you might have a 10-speed bike or something, and your brake controllers, that cable that goes, that is a woven 19-strand cable. They're very, very durable. We don't use this for cabling a whole lot in the United States, but you do see it pop up in other parts of the world. So commonly used cable size diameters are 3/16 and 3/8 of an inch. So this stuff has to connect somewhere. So when we connect it, we want those connections, or what we call the anchor hardware. So as it goes into the tree, then you're going to screw something into the tree that has an eye on it, and then you're going to put the cable in through that eye. So that point where it attaches to the tree and the cable, that's where the anchor hardware goes. And it can either be screwed into or it can be drilled all the way through. So we talk about through hardware, where it goes all the way through from one side of the trunk to the other. And then the other type is lag hardware, where it just screws into the wood itself and does not come out the other side. So here's some examples of through hardware. It should be used when dead-end lags are not appropriate. So the lags are the ones that screw in. Typically, the lags you're going to use on a lot smaller diameter wood. The through hardware you're going to use on the big stuff. So here's some examples. This is a welded eye. This is an Amen eye. So this one's a little more adjustable because this can screw on this side as well as have a bolt or a nut on the other side. You can also have all thread, which is what this is, threaded rod. It's threaded all the way end to end, just like it sounds, all thread. And so you can use this a lot longer. There's a lot less waste when you use threaded rods, because you put it in, you cut it off to the length you want, then screw on these M&Is onto the end of it. So it helps to reduce waste. So again, through hardware, there's going to be a few things just to keep in mind here. The holes should be drilled 1/16 to 1/8 of an inch larger than the rod. That's the hole you're going to drill through the trunk of the tree. So when you drill through this trunk, you're going to want the drill bit to be 1/16 to 1/8 inch larger than the piece of all thread that you're putting into it. Why would you want to do this, you might ask? Well, you want it to be able to slide. You want to be able to make adjustments. You don't want to screw it in. So when the nut's on the backside, when you tighten that up, it's going to pull the rod through without interference from the trunk. So that's called through hardware. The eye bolt or threaded rod is installed with a round washer and nut on the end of it. So you're gonna, a long time ago, we used to use these sort of diamond looking washers. Studies show that the response wood that comes about after the installation of those diamonds is not the greatest. In fact, it helps weaken the tree. So now we've switched to the round ones. The washer should be seated against the bark. Thick bark should be chiseled away. So if you're working on hollies or beech trees or maples, something that has fairly thin bark to it, you're not going to need to chisel anything out. Just have the washer and then the nut on the back side of that. However, if you're working on a cottonwood or something crazy like that, where the bark could be this thick, you're going to want to chisel down. You're going to smooth it out and get closer to the actual phloem with that. So here's some examples of dead end hardware, this lag hardware. You can see that it screws in. We would typically use these on limbs less than 10 inches in diameter. These are, we call them J hooks because it looks like the letter J. There are lag eyes. This is closed all the way. Lags come with a right hand or left hand threads. So when you're installing one of these systems, you're going to want the right hand one to go on one side and the left handed one to go on the other side. That way, when you tighten the cable, you're not untwisting the cable. You're keeping the cable sort of rotates and it's just screwing itself into the tree on both sides. So you can't use two right hand ones or two left hand ones. You have to have a right hand and a left hand in order to keep the cable from undoing itself. Seat the full length of the thread into the sound wood. So you can see someone over here is taking the handle of a pliers and putting it through the end of the J part, and they've been screwing it down. So you want this opening to be fairly level with the tree so that when the wind blows, this cable with the thimble here doesn't jump out of the J. Hopefully that makes sense. Now, again, this is not through hardware. This is going to be lag hardware. So this hardware is installed by pre-drilling a hole because these lags can be pretty big. But in this case, it's the opposite of the through hardware. Remember the through hardware, we wanted the hardware to be able to slide in and out of the drill hole. However, with lag hardware, lags is more like a screw. And so it has to be able to bite into the wood so that it screws in snugly. So here we want just the opposite, 1/16 to 1/8 inch smaller drill bit than the diameter of the lag. The lag should be screwed into the tree so that the J loop ends up vertical. So, as you're screwing it in, you want it to be like this. You don't want it to be like this. So you want it up and down. Doing these in reality, for any of you guys that have done these, you know how difficult they can be because there's all sorts of angles you have to work with when you're in trees. It's not just going to be two flat pieces like this and you're straight across. It's more likely you're going to have branches that bend over like this and ones that come back. And so the angles are going to be kind of interesting. So when the cable needs to be in line, the lags cable, the whole system needs to be in line. So because of this bend, when you're screwing it in, one side's going to hit the trunk before the other side. So you want to just screw it in far enough to where it can't jump out, but not so far that the end of the lag bolt starts scraping the bark off. Again, works well on small trees or branches, no larger than 8 to 10 inches in diameter. If you remember, our standard here is less than 10 inches. So when we use these washers, here's an example of one. Use a heavy duty round washers. Heavy duties can be grade 8 or stronger. The reason that you want a big heavy duty one is that when you're screwing it down, you don't want it to bend. You want it to remain nice and flat to evenly distribute the pressure that you're applying onto the trunk of the tree. Now thimbles, these are used to protect the cable from excessive wear, and it helps to increase the bend radius. So if I'm bending my cable around something, so if this is my cable and here's my lag, I'm going to go through it like that. So this curve that you see here, if you're looking at me on the video, this is the bend radius. So if it gets too tight, it kinks like that. And as soon as you kink the cable, it's weaker than it was to begin with. See how that's permanently deformed now because I kinked it. So what that thimble does, these are the thimbles. These thimbles help to hold that bend radius open so that it doesn't, when it's shocked, when the wind blows and it yanks on the cable, that it doesn't get pinched. And then this other thing over here, this is the quick wrap or a dead end grip. This is what, if you recall, I said this is what you use when we have the EHS cable, the extra high strength cable, because you're not going to be able to bend it around a thimble. So here's the actual cable right through here. The cable stops about right there. This is all part of the quick wrap. So you put that thimble inside of the quick wrap, and then you wrap it onto the end of the cable. Of course, you're going to want, this goes through your hardware before you close it. Some other tools that we use to help us install these things, because especially if you're working in a very big tree, just the weight of the cable itself can become tremendous quickly. It could be 15, 20 pounds worth of cable or more up in the tree. And if you're one guy trying to pull 20 pounds of cable tight in a canopy, it's going to be hard to do and get it into your hardware and all that sort of stuff. So to help take some of that pressure off, we use a come along. So above our installation point, we're going to install a come along and be able to crank it. So this handle up here, when you pull it forward, it rotates this reel and it's like a ratchet. So pop, 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 pop. So you're pulling the sides together. Once you take some of the weight off, and you don't want to take tons of weight off, but you want to take some of the weight off so that when you install your cable and then you let the come along off, the cable goes taut. Another way, or another tool, is this cable grip, this item over here. This is a cam operated deal. So the cable goes through here between this curving piece and this flat piece. Cable goes through there. You might hook on your come along, might be hooked here, or some method of attachment. But when you pull on this end, this cam is going to pinch down on the cable and grab it. So it allows you to grab the cable anywhere along the length of the cable. It wouldn't have to necessarily just be the end of the cable. Some more tools. This is called a cable aid. These come in really handy when you're installing that lag hardware where you're having to screw in those lags. You saw the other guy using a pair of pliers. Don't laugh. We've all used pliers at one point or another to put those in, I'm sure. But this is a nice lightweight tool, and it gets the job done nicely. Now, when we drill our holes to go through the hardware, or even just part of the way in where we want it to bite, we want to do is the least amount of damage to the cambium as possible. We don't want to tear that cambium as we go in. So we use a specialized type of drill bit, and it's called a ship's auger bit. You can see that it doesn't look like a normal drill bit. And this literally cuts. It's a slow speed bit. And as it moves in, you're pulling out these huge curls of wood. So you're literally cutting the wood as you go through, and it's getting ejected out the back. This makes for a very, very laser smooth cut as long as you keep these drill bits sharp and clean. So this is how the common grade cable is done. Again, here's our thimble that's going to hold this bend radius. So from this point right where the laser is to here is the actual radius. So that's the bend radius. But this is going to hold that bend radius permanently open like that. We're going to wrap our cable around it, and then we're going to pull off one of the 7 strands. And we're going to wrap that first strand around until it's totally wrapped up and can't go any further. Then you're going to pull the next strand off of here and do the same thing. And you're going to repeat that over and over again until there's no strands remaining and you have a completed eye, as you see right here. So, we talked about the woven cable a little bit, the aircraft cable. So with these, you're going to use a sort of a different method to close them off. You're going to use these U-shaped clamps to finish it off. They should not be used to form terminations on cables that are greater than 1/8 of an inch in diameter. Install 3 clamps several inches apart with the U of the clamp over the short end of the cable. Cable stops are metal knobs affixed to steel cable ends protruding through the drilled hole. So there's all different kinds of cables out now. So one of the more common ones that's out there now is you run the cable all the way through the tree, because you drilled that hole a little, 1/16 to 1/8 inch larger in diameter than the cable, run the cable all the way through the tree. And then on the other side, you have this cable stop that's affixed to the end of the cable. And then that's your piece of hardware. Cable stops are also used to protect people from getting hurt on the ends of the cable. So now we've talked about the hardware involved. We're going to skip over, no, we're not skip, we're going to go to how to install these, where to install them, that sort of thing. So you want to install the cable at least 2/3 the distance from the defect or the weak crotch to the ends of the branch. So over here in our example, so it's not 2/3 of the height of the tree, it's 2/3 the length of the two that you're trying to join together. So it's 2/3 of the way from here to the branch tip. That's where you're going to install your hardware. The cable should be installed perpendicular to an imaginary line that bisects the union. So here we're over kind of at an angle, so we're going to go straight out, and then the cable needs to be 90 degrees off of that. So again, you want it to pull nice and straight. This one, the crotch is straight up and down. We've installed it straight across, again at 90-degree angle to the imaginary line that bisects the defect. So these are J-lags. So these are the lags that are installed into the tree. And what do you see that's wrong with this? So in this example, these are not vertical. They stopped this one horizontal. Both of those, they stopped horizontally. So these should be rotated at least another 45 degrees so that they're straight up and down. It's important to have the cable pulled straight across. So just like you see here, the cable is pulling straight. You don't want to do this. You don't want to go straight through a branch and then have your cable pulling in this direction. When you do that, you have sort of a change in forces. So as you're applying a force, you have this downward force that's pulling here, which means you're going to crush this tissue here. And on the back side of it, you're going to crush this tissue here. So whereas on this one, you're going to get an even pull. Here it's going to be, the loading is asymmetric. So we don't want that. The cable should be just taut. So you don't want to be able to come up and pluck it and it sounds like a guitar string or something, but it does need to be tight enough. You don't want a whole lot of sag. Again, if you're running these things 25, 30, 40 feet, you're going to get some sag in it. You just can't avoid it because of the weight of the cable itself is so great that it's going to always flex over that distance. If the cable is installed while the tree is in foliage, it should be tight enough that when it's not in foliage, that it doesn't go slack after the leaves fall off. So here's an example of 2 different kinds of cabling systems. But the point they're trying to make here is how far up do you actually install these things? There's a guy named Klaus Medic. His books are available out there. He talks a lot about tree dynamics and tree engineering. I believe he was an aerospace engineer that decided he really enjoyed trees, so he started focusing on trees and has given us a great amount of science behind how trees respond to cable systems. So if you're putting the cable too low, remember we wanted it at least 1 or 2/3 of the way up into the canopy. So in this one, the example is, well, it's too low. So in a windstorm, trees don't move just boom like this. It's more of a chaotic motion and they do this. And they can open and close and move around. So when this canopy is moving around, if it's too low, you can actually pull the defect apart. So you get the opposite response of what you're looking for. Remember, we want to minimize, the whole reason for doing these is to minimize the impact to the point of separation down here, this poor union. So over here we have the other system, which is installed pretty far up. This might even be too far up, but this one's going to have the least amount of outward force on this one. The reason that this is kind of humorous is that Klaus Medic is from Germany, and the Germans invented this system called the Cobra system that's up in the top of this tree, and we'll talk about the Cobra system in a minute or so. Some other common types of attachments, you have direct attachments just between two limbs. Again, we are on top looking down. So if you were looking from the top of the tree, looking downwards towards the ground, this is the view you're going to get. So if you can have these four, so this one is triangular because it forms these two triangles, and then this is the box shape. And this is, again, in hopes that it all moves together, and it doesn't move down here at the crotch very much. So another one of these standards, when more than one cable is being installed onto the same limb, you want to have a certain amount of distance. Remember, or if you recall, we talked about the coded model and those walls, that wall 1, remember how it's plugging the vascular tissue above and below? So that it results in some staining. If you remember some of the photos that we saw, you saw that stain, that discoloration of the wood going up and going down from the point where it was injured. Every time you install a piece of hardware in a tree, you are injuring the tree. So you have to take into consideration what that injury is going to do over time. The possibility is that you're going to have rot. So in order to keep the distance between cables needs to be greater than the diameter of the tree. So if this is 10 inches, you want the distance between here and here to be greater than 10 inches. And if it's a 20-inch tree, you want the cables to be 20 inches apart, or more than 20 inches apart. Cables should not rub against the wood or each other. Remember, I talked about, it's not always going to be this nice straight stuff. You might have a branch like this that has a bend to it, and your cable's out here and you're cabling back. So you don't want that cable to touch anything in between the 2 points of attachment, because when the wind blows, you're going to get this sawing action. So if there's another branch in between that and the cable has to go around it, you don't want the cable rubbing on the other branch, and you don't want it to rub on another cable in case you have cables that are crossing up there somewhere. You don't want those to touch either. The anchor should not be installed into decayed wood where the decay is greater than 30% of the branch diameter. So that physical growth, it's not a chemical wall, it's physical growth, that is the strongest wall in the coded model. So once we drill that hole, we're creating that injury. And so over time, the tree's going to create this wound wood and grow over the hardware. So that growth that encapsulates the hardware is where the strength comes from. But until that stuff grows, you need to make sure and have enough sound wood in there that it's not going to fall apart. So we talk about this 30% of the branch diameter. Go back to my pen here. So if this is the outside of the branch, and we have a decay column on the inside of the branch down here, this is probably not too bad, but it's hard to tell by looking because circles grow in area exponentially. It's a non-linear thing. So you have to figure out what the area of the decay column is and compare that to the overall diameter of the branch. And that's where this 30% comes from. So if you have a branch that's like this and a decay column that looks like this, might even go all the way to the outside, something like that, this would not be a candidate for putting through hardware in because the shell wall is just too thin. So this one would still be a viable candidate to go through the center of this one and put your hardware in. Another thing to remember is you don't want to put more than one cable through any one attachment point. So only one cable per point of attachment. Again, much of the holding power comes from the wood that calluses after the installation. Cables must be inspected annually. Cables may need to be installed higher as the tree grows. So this is part of that arborist responsibility. When you sell these products, you have to notify the steward, the landowner, that these cables need to be inspected. And it's rare, well, I say about 50% of the cables, people will say, oh yeah, we want you to come back out every year. Because what do you have to do? You have to pay somebody to come out and take a look at it. So by installing these, they are taking on a responsibility that says, hey, I'm going to hire you every year to come back and inspect these. Doesn't always happen. So because it doesn't always happen, in your verbiage, when you install these, you should have some type of release of liability saying that if they don't have you back out every year, you cannot be held responsible for what happens to the tree. And you might also be working with small trees. So as the tree grows taller and taller, you might have to reinstall cables higher into the canopy so that you still stay that 2/3 of the way out from the defect. So we've talked about cabling. Now we're going to talk about bracing. One of the important things to understand about bracing is that it's always done in conjunction with cabling. Cabling can be done by itself. You can cable the tree and nothing else. However, if you do bracing, you're going to have to put in your brace and a cable system. So it's always cabling and bracing together when you're using bracing. And here's the brace on this tree, goes all the way through. This is all thread. So you're just, instead of using any type of cable, it's just all thread the whole way. It's always used in conjunction with cables. Lag threaded rods, wider and deeper threads. Machine threaded rods, narrower and shallow threads. So you might see what is a lag thread on the exam, and that's going to be a very coarse thread. So the actual helix that goes around the centerpiece is going to be wide open, and it's usually going to be pretty deep because it's screwing in like a regular wood screw. Machine threads, the threads are very close together and they don't go very deep because you're not biting into the wood. The whole point behind the machine threads is that it just holds the nut. So here's an example of where you might do some bracing where you're just using threaded lag, where you're just going to try to screw these two together. And again, you're only going to see this on really small trees. This might be something you would use on a Japanese maple or a dogwood. It is not something you're going to use on a huge mature oak. So again, you want it to bite. So you want, as you're screwing this lag in, you want it to bite. So the pre-drilled, the pilot hole needs to be 1/16 to 1/8 inch smaller than the rod. The advantage is that here the threaded rod itself is what's providing the support, just like screwing two pieces of wood together. The machine threaded rod should be used in larger trees or trees that have soft wood or decay. So if we go back and look at this one, if this was a big hollow area on the inside, then it's like right here, if this was all hollow, then this guy's not going to hold very well because there's no holding strength there. Hopefully that makes sense to you. A single rod should be installed above the crotch at a distance of about 1 to 2 times the branch diameter. So here, if this is 10 inches in diameter, you go up 10 inches here or 20 inches here somewhere. And then you're trying to, it's not so easy to do it, but you want to drill straight through the tree. So you're going to drill here. It's going to be one drill, and they actually make drill bit extensions. So you have your ship's auger bit, remember, and then you're going to use these extensions. So if possible, use the extension so that you get a perfectly flat line going all the way across. It's not as easy as it might sound to get those lined up. Then once you've installed it and you've put in your washers and your nuts, cut off anything that's left over out here. And remember, when you cut it off, the threads are still there, so you could just remove the nut, but we don't want the nut to come off. We want it to be permanently there. We don't want it to shift or move on there. So we're going to do what's called peening. So we're going to peen the end of it so that it can't back off. So here we see the word peen. So you're basically just pounding the ends of these threads with a hammer so that you're collapsing the thread so the nut can't back off. So I was driving around looking at jobs and I saw this one and I just had to get out and take a picture. So this was a homeowner's attempt to do bracings. So, you know, how many problems can you find here? I wish we could be interactive so you guys could tell me what you're seeing, but let's just go over a few of them. Here we have a square washer. Remember, we want a round one. And then look at the angle here to here. So notice that the force is pulling downward. It's not a straight line pull. They did not cut off the ends here. So the ends did not get peened. They didn't even use cable. They just used a big turnbuckle in here to try to pull the two together. And this is a pretty sizable defect. You can see that split here. You can sort of see that split as it curls down the tree. It is a pretty significant split. So that's the worst of it, right? So now we're going to talk a little about the dynamic cable system. So dynamic means it moves, it's changing, it's not static. The other ones are referred to as static installations. The cable's a fixed length, it doesn't move. We want it to be static. However, this were the dynamic systems, and there are two types. The one I spoke about earlier that's made in Germany called the Cobra system, and there's one in the United States called the TreeSave. There might even be more of these now. This presentation has a little bit of age on it, but it allows for the tree to move. So with the other cable, when the tree comes apart and it can only go to the length of the cable. So if the wind's blowing like this, it might collapse the cable, the wind stops and it pops back open. So the point where the cable is attached becomes almost like a tuning point. So if you think about a guitar string and you pull a guitar string and you put your finger on one of the frets, you can change the frequency of the string right. So we don't really want that to happen in our tree. So the way to get around that is by using these dynamic systems, because the dynamic systems move. So it doesn't focus the force, or like where you pinching the string to the fret. You're changing the length of that cable, but you're focusing the force here instead of out at the end of the guitar where you might tune it. So same sort of thing here. We don't want to necessarily focus all that force right where the anchor point is. So if you have really violent winds with these things in, it might not fail at the crotch. It might fail where that anchor point is. So what Klaus did was he said, I think if we use a dynamic system, we're gonna be able to load the tree with wind and unload the tree with a much smoother action. So this stuff it's polypropylene rope. So you can see it here, and it's hollow. It's built kind of like the Chinese finger puzzles where you push it together and you stick your fingers in and then you try to pull your fingers apart and the the puzzle shrinks down on your fingers and you can't get them. So that's how it works. So when you compress it, it opens up. So when you install these things, you compress it and you put this big rubber tube on the inside of it. So you can sort of see that fat spot right here where the laser is. That's called a snubber. And so what happens when the wind blows is it pulls on this and it pulls down on that snubber, and it's kind of acts like a bungee cord. So the rope itself doesn't flex much. It's the collapsing on that snubber is where it gets that sort of cushion, like a damper. So it's going to go out, boom, and then slow down and then come back together. So the other thing here is you notice that you didn't drill into the tree. So there's no permanent hardware attached. So every so many years, you can come out, remove this stuff and run it higher into the tree and continue to have your 2/3 of the way up. However, you have this maintenance issue. because we're going around the trunk, we don't want that secondary development to begin to incorporate it and destroy our vascular tissue, right? So you're going to have to go and move this thing a little bit every year to keep the tree from incorporating it as it grows. And I've talked to a few people who use these systems consistently. They're fairly easy to install. They last a long time. There is a coating, or not a coating, it's an additive to the polypropylene that makes it highly UV resistant, because that's normally what would erode, as sunlight would normally erode the integrity of this stuff. But they say that they're getting 10, 15 years out of it, and it's still very functional. Now we're going to move on to guying. So remember, guying is an external attachment. So we have our tree, and then something external to the tree we are anchoring to. This is going to reduce the tree movement. It'll be able to move towards the anchor a little bit, but it won't be able to move away from the anchor. We installed tons of these things on on Leyland cypress, because Leyland cypress only has 3 or 4 main pedestal roots, and the distribution of those pedestal roots is pretty random. So they can't actually all show up on one side. So you have 3 pedestal roots on one side, no pedestal root on the other. And so in any type of storm, it's going to fall in the direction where there's no pedestal root. So we would use external guys to permanently hold them up. So the guy wire should be attached to the tree at a height at or above midpoint, or 2/3 the height of the tree. So we want to get greater than halfway, but less than 2/3. So another thing to keep in mind, especially if you work for a city, if you're installing these external anchor points, you still need to be able to maintain turf under here, or whatever's growing under it. And you also don't want to create a choking hazard where kids are running around, they run behind a tree. So we would normally only use these like in DOT areas or places where there's not going to be any foot traffic. However, if you're using it in a park, you might want to not have this direct attachment to the ground. You could put in a significant post over here and then cable it to the post instead of having this angle, because this does make somewhat of a risky situation. The ground anchor should be placed no closer to the trunk than 2/3 the distance from the ground to the lowest attachment in the tree, as shown here. So it's pretty, guying is it's pretty straightforward. There's again, we have the same anchor points that we've talked about before. Make sure that this anchor point, that the angle of that anchor point is going through the tree at the same angle that it comes off. So again, you're not having this horizontal or piece of hardware in the tree that's being pulled down. So you want it all to be in line going through the tree. And so last, we'll talk about propping. Propping is starting to catch on more and more here in the States, but it's been used in Europe for a very long time. So propping is the installation of a rigid structure between the ground and a branch or trunk to provide support. For those of you that are in the metro Atlanta area, if you go to Norcross and go over to City Hall at Norcross, you'll see this giant American elm, and they've done a pretty good job of using props on that tree to hold some of the larger branches in place. So these are the props that you see sticking upwards, and these have sort of a cradle at the top of them so that the branch sits in the cradle. They can have carpeting or something soft and fairly UV resistant as the padding inside of that sort of saddle. There's different kinds of props. These happen to be the type that are flexible. So there's a pivot point down at the bottom here, and they have these cables. You see, sort of see this crisscross of cables underneath. But what that allows it to do is it allows that prop to flex a little bit so that you're still supporting the branch, but it's not just fixed. So most of them they're set in concrete. They don't pivot. And so the branch just does this, or it has to rub around on that saddle a little bit. With these, it all stays sort of one piece like that. All right, so do we have, I know this is one continuous presentation here, the lightning protection, but that sort of finishes the cable guying and propping and all that sort of stuff. Okay, so we'll get on to lightning protection. this is a great photo, and there's more and more photos and clips and stuff coming out now. You can go on YouTube and see these trees that get struck. The amount of power in a lightning strike is just almost unfathomable. It is tremendous amount of energy released. So where does lightning strike? Lightning may strike a tree, travel down the stem of the tree, then leave the tree, jumping to a more conductive tree or structure or person or animal in what's called a side flash. So lightning can go in both directions. Lightning can emanate from the ground and discharge up into the clouds, as well as being from cloud to ground lightning. So as lightning strikes the top of the tree, it's going to travel down. If there's something that is less resistance, because wood it's a fairly good insulator, so it doesn't necessarily want to travel through wood. So if there's a clothesline, a metal clothesline or something attached to it, it's going to jump off of the trunk onto that metal clothesline and go discharge somewhere on the metal clothesline. But that sort of coming off, that's referred to as the side flash. Lightning exits a tree through the roots and dissipates into the soil in the absence of one of these side flashes. So it dissipates into the soil eventually. That's a literal grounding. So when you have lightning, the damage can be very minimal, or it could be a lot of damage. It can blow like all the bark off the tree all the way down to the cambium. So it can be really tough, or you can just see this really fine little line that comes down the tree. We're not real sure what things are at play there to make such a big difference, but it's obvious that difference occurs. So if you have one of these tiny little stripes, that doesn't mean that it didn't destroy the root system. So dig around the base of the tree and see how much the root system was damaged. We're going to talk about step voltage. This is a difference in electrical potential. It occurs at the soil surface as the charge dissipates. So see if I can make this work. So here's an area on the ground, and then here's an area a little further away, and an area a little further away, and an area a little further away. So if it's 100, if it's 1,000,000 volts right here, some step away, it might be 500,000. Another step, it might be several thousand. Another few steps, it might be into the hundreds. And so you have 100-something volts here as compared to almost 1,000,000 volts here in the middle. So that the distance away is the step voltage. So it's going down as you step away from it. Current moves wherever there's a difference of potential energy. So if you just have your car batteries, got the positive and your negative, and they say there's 12 volts there. So the difference between this pole and this pole is 12 volts. If there was no difference, if it was a 0 voltage battery, the two would be right next to each other. So if you hook something up on the positive and you connect it through some circuitry back to the other one, you're going to have current flow. And depending on what the resistance is in the circuitry out here, the current can be really high or the current can be really low. Keep in mind, voltage is not what kills you. Amperage is what kills you, and that's the flow. So if you were in an area that got struck by lightning, or you have a cable that dropped down onto your vehicle and it goes out, a charged energy line is on your vehicle, you can't just jump off your vehicle, because as soon as you start walking away from your vehicle, you might put 1 foot here and 1 foot here as you walk away. And now you have this tremendous voltage difference. Remember, this one was like 500,000 and this one was like 100,000. So you become the circuit, you're the circuitry. So the current's going to run through you and you're going to die. That's just the fact of it. So, but if you kept your feet together and you bunny hopped like this away from the area until you're in an area where there's no more dissipation, then there's going to be 0 voltage. If your feet are together and you're not stepping and you're just hopping off like that. But always wait until an energized conductor is no longer energized. So wait for the power company to come out and shut it off before you start jumping away. So we'll talk about this again in the climbing section. But step voltage, I don't think pops up again in there, but I wanted to explain that step voltage is also important when it comes to things like aerial rescue or getting off of a bucket truck that's energized. So where do we want to, what trees are susceptible to being struck by lightning? Well, it's the tallest tree in the group is pretty susceptible. Trees growing out in the open all by themselves or in small little groups are susceptible. Trees that border the forest, those are susceptible, or along the streets. Trees close to water, trees on hilltops, trees in local areas or geographic regions with a history of strikes, and trees with cables. So it's starting to sound like every tree could potentially be hit by lightning, and that's true. But in general, the tallest in the group, or the most isolated, the more isolated the tree is, the more likely it is to be the one that gets struck. And also, contrary to popular belief, trees do get struck over and over again. So when they say the geographic regions, for those of you that are in Atlanta, Mount Perrin Road it's a basalt flow between two granite outcrops. And as a result, we call that Lightning Alley because there's more lightning strikes down Mount Perrin than just about anywhere else in the city. Trees with cable systems, and not just cable systems, but low voltage lighting systems, swings, any number of metal objects that are in these trees can also encourage a lightning strike. So what trees should have a lightning protection? So that's where we're headed with all this, is that we want to install an LPS, a lightning protection system, so that we can not have the bark blow up, so that we can somewhat control the dissipation of energy from the lightning strike. But it's not cheap. Any of you that might have experienced stolen copper lines from a house or construction sites know that it has a lot of value to it. So as a result, the hardware is quite expensive. So not just anybody's going to want to put these in, but you might see them in historic or landmark trees. Trees that are within 10 feet of a structure are a good place to install them. Trees where people seek refuge, like on golf courses or parks, and large trees that stand alone. A typical lightning protection system on a house might be $50,000 or more. A lightning protection system on a tree might be about $2,000, $2,000 to $3,000, depending on how big the tree is. So if you have a tree that's within 10 feet of your house, if you install the lightning protection system in the tree and you're dissipating it away from the house, you're going to reduce the likelihood that your house gets struck by lightning, and you wouldn't need to spend $50,000. Golf courses, all PGA golf courses have lightning protection systems on the tee boxes. And you might think, wow, how considerate of the PGA. Actually, it's not for people, though. It's for the camera equipment so that it doesn't damage the hundreds of thousands of dollars worth of TV equipment. So what does this hardware look like? This is the copper conductor. We call it a down conductor. And notice it's pretty open weave. If you were to play with this stuff, it almost looks like it falls apart in your hand. And the reason is that we want the lightning to travel on the outside of it like a halo. The intensity of lightning, there's almost not a cable that's going to conduct it. So what we want to do is guide it. So instead of the electricity going through the cable, it travels around the cable. So this lightly woven copper helps it to do that. It helps it to travel in a halo. All the protection hardware should be approved by the National Fire Protection Association or Lightning Protection Institute. Sounds like that could show up on a test somewhere. So the uppermost point of a lightning protection system is the air terminal. This is the terminal. This is the part that you want as high up as you can get it. This is the part that's going to attract the lightning. It is attached to copper cable by using barbed copper nails. So you see this whole thing is several parts. It's one entity, but it's several parts. So this is a copper piece, or it might even be copper clad over something harder like stainless steel or something, but it's copper clad. And this section is also copper, but this section is brass. You might say, well, why is part copper and part of it brass? Brass is more resistant to electricity than copper is. So by using these two different types of metals, the lightning is going to travel down the copper and not going to want to travel down the brass. So that's what holds it off of the tree. And then this is a nail. So when you're installing this up in the top of the tree, this little foot area here has a hole in it. And so you take these little nails and you're nailing them into the tree. This thing, these are the copper teeth up here. You're going to take that woven, you're going to take this stuff, and you're going to lay the end of it in there, and then take a pair of pliers and crimp those ends over. So it's like this, and then you crimp it over like that and holds the cable in place. Again, air terminals should be located near the top of the leader and out most of the major branches. They do not have to extend beyond the branch tip. It is copper so much more conductive than the tree is that it's going to not go for the tree. The lightning is going to come in and hit this air terminal before it hits the branch tips out here. So you just have to be close. So when you're climbing and installing these things, typically in an oak tree, you'll tie into something about the same diameter as your wrist. So if you're tied into something like that, you reach over your head to install the terminal, that's plenty far out. You don't have to do anything extraordinary to get all the way out to the branch tip. However, as the tree grows, you might have to every 7 or 8 years move that terminal further and further out. So the main conductor is a copper cable that is attached to the tree at regular every 3 feet. There's going to be a little stanchion. So it looks similar to one of these. So this is what stands it off of the trunk of the tree. So that's the stanchion. But instead of having the air terminal on it, there's just going to be a little saddle there that you can crimp over and they're all going to be brass. So even the piece that crimps over the top is brass. So again, they're going to attach these every 3 feet or closer. So if you have a branch like this and you have a trunk like this and you're running your cable down the side of it, well, if it bends, and I have one here and one here, as it bends, the cable is going to get closer to the trunk, right? And so you'd have to add another stanchion off to hold that cable further off the trunk. So maybe I can make that a little clearer. So if I have a curving branch like this, and I have a stanchion here and a stanchion here, if I drew a straight line, the cable is going to touch the trunk of the tree. So to keep it from touching, I'm going to have a stanchion here, one here, and one here. So it's the same 3 feet, but now I'm keeping it further off of the trunk, right? So you don't want that cable to ever touch up against the trunk. The conductor should also allow the tree to sway. So if it's moving in the wind, you could have the same sort of thing. So even though it's a nice straight piece and you've got a stanchion here and a stanchion here, if the wind blows and it's going to do this, that cable is going to get pulled into the side of the tree. So put another cable here, and you could even leave a little slack, just as long as it doesn't touch the trunk of the tree. So just take into consideration the sway of the tree when installing it. Ground terminal is installed to provide electrical contact with the ground. So just like it sounds, we want to ground out all this potential energy into the soil. And we don't want it to be right at the base of the tree where it's going to damage, it would still damage the root system of the tree. So when we're placing these ground rods, we want them to be, you have a question over there?
I do actually.
Okay.
Wants to know, is that the ANSI spec again now for air terminal installation?
For as it pertains to the distance outward, or the only real thing that's changed is we used to use 2 different sizes of cable. Now it's all one size of cable. You don't have to use big stuff and little stuff anymore. It's all one size. but the distance out, that's the best management practice, the BMP from the ISA. There is an ANSI standard for it as well, but it's taken directly from the Lightning Protection Institute. But I don't believe it's been updated any more than that. Is that the question?
I believe so, Jeff. If you have any further clarification or questions, please let me know.
Okay, so ground terminals consist of a ground conductor or ground rod, plate, or associated connectors. So we're going to put these things into the ground. They're pretty long pieces, and you have to drive them down. So if you've done much groundwork in Georgia, you're gonna realize that at some point you could run into a rock and you're not going to get the full length of the rod into the ground. So we'll talk about different ways to do that. Yeah. So when 2 or more trees with protection should be connected to each other. So if the trees are close enough to like their canopies overlap or something like that, if you're installing it in this tree and you're installing it in this tree, you want to hook your system up so that it's one continuous system. So here's an example of the air terminal here. And he's got an air terminal out here. You know, at some point they might even put another one out here as it becomes another major lead. So we're gonna run this stuff down the trunk. Notice they're saying that these stanchions are 3 to 6 feet apart. You can get them closer again in areas where it could bend. You want to join anything that's metal in the tree. You want to pull it into the system as well. So here's a cable that someone installed to take the stress off of this. So we're just going to run a copper line from the cable itself over to our down conductor. The cable should come off of the tree trunk, and once you get out, buried 8 to 10 inches below the soil and then grounded. So this area should be slightly underground, 8 to 10 inches. Now this is greater than or equal to 10 feet. Personally, I like to have it outside of the compression plate. So if you have a very large tree, you might have a compression plate with a radius that's 15, 16 feet in diameter. So you'd want to try to put the ground rod further out than that, but the standard is greater than or equal to 10 feet. You have another question over there?
Jeff wants to know, he says, I believe that the grounding has to be done with a specific length of rod, but it can be cut into shorter pieces and interconnected by cable.
Yeah, and that's what we'll get to here in just a second.
All right, thank you.
So the ground rods, I can't remember if they're 10 feet or 12 feet long, but they're pretty long. So if you have soil horizon like this, and you have some rocks down under the ground somewhere, if this distance is about 6 feet and this one's about 7 feet over here, you can install the ground rod until you hit this rock. Then you would cut it off, and then whatever parts you didn't get into the ground over there, then you would take it and drive it into the ground over here. And then there's a cable that connects these two together so that you still have, because it's about the volume of soil. It's called a dissipation cone. So the electricity is dissipated into the surrounding soil around these ground rods. So you want these things to be greater than 10 feet apart, so that they're not dissipating into each other. You want 2 totally separate dissipation cones. And there are places where you won't be able to get any ground rod in. So the next time you go up Stone Mountain and you go look at that big tower on Stone Mountain, you'll notice that there's a chain link fence around some of these big heavy duty steel plates, like the kind of plates you see the DOT use. They take those plates and they literally bolt them to Stone Mountain. And then they take the lightning protection system that's on that tower, run it out and connect it to that plate so that it's dissipating. The dissipation area is that plate. So Jeff, yes, you are correct. That's how you have to do it, so that you have the same amount of dissipation area. Air terminals must be extended as the tree grows. Lightning protection should be inspected annually and maintained as necessary. Again, this is something that is a liability for the person that installs it. So when you install these systems, make sure that you have some verbiage in there that gets you back in for the annual inspection, or verbiage that releases you from liability of having to inspect that every year. Because these things, I talked about the PGA. So the PGA wrote a specification and said, okay, all tee boxes must have lightning protection systems in adjacent trees. That's all it said. So it never said go back and make sure they continue working. So all the ones that were installed in the early 90s, you go back and look at these golf courses and there's just stuff blowing in the wind. They've broken apart. They no longer function because it was never written into the spec. So if you work for a municipality and you're installing these things, make sure that you have a perpetual budget for inspection for as long as the tree lives. So if you guys have any questions over this part, again, shoot me an email and I'll be happy to answer questions that way. So whenever you think about them, not just during the course. I still get emails from people that took courses several years back that just want some help. So I'm always around. Now it's break time.
Thank you. Thank you. Yeah, I remember I did this last time too. So thank you for calling me on it this time.
Yeah, no worries.
Everyone, it's time to take a 15-minute break. It is 10:11. So be back at 10:22, please. Is that right? No. 15-minute break. Let's just go ahead and say be back at 10:25. Is that okay? For the extra 1 minute to go away. So 10:25, everybody be back.
It must have been cold there in my shadow to never have sunlight on your face. You were content to let me shine. It's your way. You always won't step behind. So I was the one with all the glory. Now you were the one with all the strength. You face without a name for so long. Beautiful smile to hide the pain. Did you ever find you for the wind beneath my wings? Might have appeared to go unnoticed, but I got it all here in my mind. I want you to know I know the truth. Of course I know I would be nothing without you. Did you find forever my way? Did I for the wind beneath my wings? You are the wind beneath my wings. Oh, my wings. Thank you, thank God for you, the wind beneath my wings. Oh, I feel it in my She gives me high, I want to, she gives me cuckoo sweat. God, relax, you can't all my tracks, get back to me. Take on a ride on the moment, back to the break.
Alrighty, folks, if you are in earshot, go ahead and let's get settled back in. Get ready to listen about plant health care. That's chapter 11 with Rob. We are getting started here in just a moment. Rob, you got a comment in the Q&A that somebody remembers you when you worked for Spence and Kevin. So just bring that.
Yeah, that's been a while now. You know, when I worked for Spence, that was 30 something years ago now.
Wowza. Who knew you were that been around that long?
This is actually my 33rd year.
Wowza.
31st year of being a certified arborist.
Man. Fantastic. Well, hopefully we're going to have some join you after this class. Everybody, time to get started again. I'll hand it back over to you, Rob.
All right. So are you looking at the right stuff still?
Yep. It's perfect.
Okay. All right. So we're going to get into plant health care now. Some people just call it PHC. And this is something that came about, probably started during the time that I've been an arborist. We used to have IPMs, and we'll see how that sort of morphed over time into something else. But this is most of what I do, or about at least half of what I do, is plant health care in my business. That the other half is consulting as it comes to construction related activities and business operation. So we'll jump into chapter 11 here, plant health care, and we're also going to talk about integrated pest management, IPM. Again, this is sort of where plant health care came from. We're going to talk about what defines a healthy tree, what the appropriate response process is, the allocation of plant resources, monitoring programs, pest management options, and preventative strategies. You know, the objective of plant healthcare program is to really minimize interaction with people. We want to reduce the need for pesticides in the environment. We want to reduce the demands for water. We want to reduce the likelihood of pruning, things like that. So plant healthcare is not only about chemicals. A lot of people think, well, plant healthcare, it's all about chemicals. No, it's about keeping the plant healthy. And so keeping the plant healthy might also include some pruning. You know, if you're trying to reduce the likelihood of a split, or you're trying to do some reduction pruning to establish apical dominance on a single stem, something like that would also be included in a plant health care program. So they are sort of holistic, comprehensive program to manage the health, structure, and appearance of plants in the landscape. Reduce the use of broad spectrum pesticides. You know, there are pesticides out there that are hyper specific, like just the eggs of mites. It won't kill anything. It's just a mite ovicide. That's pretty darn specific. We'll also talk about managing the cultural practices of the landscape and how that impacts the health, growth, and development, how it interacts with turf and shrubs. And so PHC ideally will begin with the design of the landscape and selection of the plants. We want to have plants that have the potential to have vigor. Like just because live oaks live here in central Texas, we now know that it can get cold enough here to damage them, but still this is their typical range. We wouldn't go up to Minnesota and expect these live oaks to live. So they are not going to have vigor in Minnesota, but they can have vigor along the southern coast of the United States. So make sure that you're dealing with plant material that should be there. And so it's sort of the right plant, right place sort of thing. So once you have the right plant in the right place, what's going to keep it healthy? You know, a plant is considered healthy when it's free of disorders and pests and has sufficient ability to resist stress. Vitality, this is an individual plant, a plant's ability to deal effectively with stress and thrive in its given environment. The vigor is the plant's inherent genetic capacity to resist stress, environmental stresses, or insect and disease resistance. So trees have, you know, we've talked an awful lot about how much energy a tree makes. You remember those hundreds of thousands of calories an hour that an oak tree can manufacture. So all that energy is either stored or it's used for something. And it's not always used constantly in the same manner. So we talk a little about phenology, and we'll talk about that a little later. But the four primary functions of resource allocation by trees are maintenance and reproduction, growth, storage, and defense. So just think about how much energy it takes to reproduce. Flowers do not contribute to photosynthesis. So they are going to consume energy to manufacture the flower. They're going to consume energy to manufacture pollen. Now just think of what Atlanta is like in the springtime, and there's just this yellow coating over everything. That's a ton of calories. And then think about the seed that's produced, whether it's, you know, a giant acorn from a overcup oak or something like that, you know, down to little tiny seeds. But all of them, there's an enormous amount of energy stored in there. I mean, just think of how many calories are in a handful of walnuts. There's a lot going on there. So that's one place that energy pretty much has to go. Growth, we have, remember the primary growth, so we have shoot elongation in the spring, and then we have secondary growth that pretty much occurs throughout the growing season. And then we have that live xylem tissue in there that's maybe no longer conducting up and down, but we still have the rays and the parenchyma cells that go in and gather those stored starches, brings them out to the active vascular tissue. And remember, that's a process that consumes energy. So to get energy packed in there, took energy to get it there, and it takes energy to get it out. So that's an allocation here, the storage. It's not passive. It requires energy to make that happen. And then defense. There's a number of defensive mechanisms that trees can make. There are a few chemical defense mechanisms like tannins that are produced out there. There's phenols that are produced out there. There's also thorns might grow on the outside of the tree, or it might grow an excessive amount of bark. All these are required energy to manufacture them and to sustain them. Now, this varies by the season, environmental conditions, and genetic strategies. So, you know, we talked a little about compartmentalization. What we didn't really bump over during compartmentalization was that some trees are inherently better at compartmentalizing decay than others. In general, the faster growing the tree is, the less it has in defenses. The slower it grows, the stronger compartmentalizer it is. You know, white oak grows fairly slow. It's a great compartmentalizer. Paulownia, tomentosa, not so great at compartmentalizing. So it just says, to heck with that, I'm going to grow faster than any decay can catch up. So fast growing is its defense. Also, mild stresses can redirect resource allocation to increase drought or pest resistance. If the tree's picking up on the fact that there's not as much soil moisture there, it might reduce the amount of energy that it's using, redirect it from, say, growing a whole bunch of new leaves to maybe growing some more roots to compensate for not being able to get enough water. If I get attacked by a few caterpillars that start munching, triggered into producing chemicals that aren't so tasty, these tannins that get into the leaf that make them less tasty. And in fact, you can have those through the mycorrhizal system, that one tree can actually say, hey, I'm being munched on. And that same stimulus chemical can travel through the mycorrhizal relationship into an adjacent tree. And the adjacent tree can even start to produce extra tannins in the leaves before the caterpillars even get there. So kind of cool stuff. Some, the plant's defense mechanisms, we'll drill down, look a little closer at that. So the physical deterrents, again, we have the thorns, the spikes, hairs, thick cuticles, cellulose, and lignin. We use in the industry a product called paclobutrazol that slows growth down. It inhibits that primary shoot growth in the spring. It reduces it tremendously. But another byproduct of the product is it makes a much smaller leaf. And by making a smaller leaf, it still has the same volume that it did before. So if we did volumetric measurements on it, the volume of the leaf would be about the same. But since you're making a smaller leaf and you still have the same number of cells, you have all the hairs on the bottom side of the leaf now are 33% more dense than they were before the treatment. And you might say, well, what does that matter? Well, there are some fungi that get caught up in those hairs. They're small enough or the hairs are dense enough, they get caught up. So what they found that, the use of some of these products actually improved, pest resistance. That's kind of a neat byproduct. But some trees just on their own manufacture a lot of leaf hairs. Thick cuticles, like you see on the magnolias, those things are pretty durable. Cellulose and lignin, these are what makes the cell walls and what makes them strong and flexible. So there are, that's part of the defense that's built in. And then the alleochemicals, we've already talked about tannins and phenols. Phenols are going to pop up when you do pruning at the branch protection zone. Chemical deterrents to herbivores and other pathogens. So there's a lot of pesticides out there that are derived naturally. And for those people that smoke out there, again, nicotine, neonicotinoids are one of the greatest, or most, not greatest, but one of the most impactful insecticides on the market. It is highly systemic. It does a very thorough job of killing things that feed on the tree. But this nicotine comes from the tobacco plant. It's naturally produced. You have pyrethrins. These things are naturally produced in the environment, and then we synthetically copy them to make insecticides out of them. But these plants can produce them totally naturally. And because of this, there might be some development of a caterpillar of some type that is immune to nicotine. And so it's going to attack those tobacco plants. So that's just a quick example of a reason most insects are host specific. So aphids you might find aphids on all kinds of plant material, but you look at something like an emerald ash borer and you're not going to find an emerald ash borer on an oak tree or a pine tree or any cone-bearing tree, stuff like that. So they're going to be very specific. Rapidly growing trees are sometimes less resistant to certain insects and diseases. So if it's attacked, I might not be able to make all these chemical changes to avoid the attack. But again, going back to the Paulownia, Paulownias can grow extremely fast. And so its defense mechanism, instead of making these chemicals, it's just going to divert photosynthate from defense to growth. So it's just going to spend it all on growing more plants so that it can even outgrow not only a a pathogen, but outgrow an insect as well. So this is sort of what happens in a plant in response to the stimuli that it experiences on the outside. So if you have a limited amount of water, the tree is going to start a response to the drought. And the first thing it's going to do is it's going to close down the stomata on the bottom side of the leaf. So the stomates are going to get smaller or close altogether. The cells are going to change turgor pressure. So after it's closed and I'm still having to use all this moisture, so as the moisture is given off or consumed, the leaf begins to wilt. If this happens over a long period of time, you're going to have an increased root to shoot ratio, meaning that the plant's going to reallocate energy from doing other things to growing roots. So it wants to grow as many roots as possible in hopes that one of those roots out there becomes successful and finds moisture and helps me to overcome the drought problem. In extreme cases, the tree can just drop the leaf altogether. So from a historical standpoint, things that are pioneer species of trees like pines, poplars, sweet gums, river birch, things like that, these older ones can actually just shuck the leaves off because, think about a tulip poplar leaf. It can be pretty large. They're really kind of papery thin. They can lose a lot of moisture. Typically, these trees would grow in a wetland environment, and so moisture typically wouldn't be a big issue for them. However, when they do go into drought, it would rather pop the leaf off than try to close all those stomates because the leaf's so big and so unprotected that it liberates too much water, so it's just going to drop them. But that's a perfectly normal response. Same thing with the river birch. You get calls in late August or mid-August, sometimes even into July. People are saying, my river birch is dropping leaves, it's dying, when in fact it's just trying to protect itself. It's not really dying at all. So a response to light. This happens a lot in construction. It also happens in what we call the urban valleys. If you go into downtown, any major metropolitan area that has skyscrapers and stuff like that, the amount of time that the sun is actually directly shining down onto the trees might be only a few hours a day. And so if I'm not getting enough sunlight, but I'm getting plenty of moisture, what do you think the tree needs to do? It needs to put out more solar panels, right? It needs to add more leaves. So to do that, you're going to get more shoot growth. And that would likely be at the expense of less root growth. So here you're going to have all this new shoot growth to help increase the number of leaves, the size of the leaf itself. And it's kind of fun to go out into the woods when you go on a hike and look for southern red oak or northern red oak leaves, because they're very dramatic. Down in the shaded part of the forest on the lower branches of the northern red oak, you might see leaves that, bigger than your face, these huge things. And then on the same tree, you can go to the top of the tree and you see these very small leaves at the top. That's because the bottom is trying to compensate for the shade by growing a larger leaf. So again, in a plant healthcare environment, what does this mean to us? The tree needs to have a certain amount of sunlight to be happy. And again, I spoke a little the other day about this sort of 10 by 10 spreadsheet that I recommend everybody build over your career, where you're listing out what the species are common to you, what they need to be healthy, what kind of soil pH, what kind of water requirements, what kind of sunlight requirements do these trees have. By knowing all that, you might not plant a tree that needs a lot of sunlight in one of these urban valleys that's only going to get a few hours a day, because no matter what, it's going to be a constant stressor because it's never going to be able to manufacture enough photosynthate. And it's going to be at the expense of the root system. So just keep that in mind. Another limiting factor that we talked about on Tuesday was the nitrogen, what happens in a nitrogen deficient environment. So you're going to have a decreased shoot growth. So it obtains nitrogen from the soil. And so if it's obtained from the soil, whether it's nitrogen, water, any of those sorts of things that you find in the soil, if it's there, you're going to have increased root growth and decreased canopy growth. So you're getting plenty of sunlight. The problem is not enough nitrogen, so it's going to grow more roots. And the leaves can actually become smaller and thicker. Again, you can look at these as stressors also. So if these smaller, thicker leaves, that is a stress response. So it's spending energy. So it's not only reallocating energy that would have been used for both shoot growth and root growth, one over the other. So eventually that becomes a chronic stressor. It's like a tree that's in that urban valley, not getting enough sunlight every single day. That's a constant stressor. So we can take any of these stressors, like limited amount of water, limited nitrogen, and put them together. And when we put them together, we get multiple stresses. Multiple stresses will cause a state of decline. And it could even precipitate the mortality spiral. Options for reversing the effects at that point are really pretty darn limited. Yeah. So the plant healthcare process, it has a lot to do with communication and terminology, and it happens a lot in our industry where we learn about these things and we forget that perhaps the owner of the tree doesn't always realize these things. So we need to learn how to establish a vocabulary for these topics and have it be fairly consistent and be able to communicate that easily with your clients. But a plant healthcare program begins with monitoring. You want to go out and observe the plants in the environment that they're there. You want to identify the actual species of the plant. You want to identify any pests that you see quite accurately. And you're going to record these things that you see and analyzing both the plant and their surroundings and the landscape. So remember, you can't really just isolate it to the plant. What about the environment also? Irrigation is one of these things that people love to irrigate their turf, and then they also put irrigation on their trees as a separate sort of a flood. Normally would only be used for the first year or two during installation of the plant, then you would shut that one down or close it off. But if it stays open and you're irrigating the turf, you can create too much water and create a problem. So don't only look at the tree or the natural things, you also have to include the parts of the landscape. Was it terraced? Is there irrigation on every terrace? Did they want to leave a tree and they built the terrace around it so the actual root plate's 5 feet deeper than what it looks like? Stuff like that. So try to absorb as much as you can about the actual hardscape, the landscape, as well as the plants that have to survive in it. This allowed, by knowing all these things and continuing to do that over time, where you're going back looking at these same things over and over, you begin to develop a longitudinal picture. Why is it responding this way? What are the key plants and what are their stressors? In a plant healthcare environment, you have the type of client that wants the nuclear option. They don't want a single pest anywhere on their whole property, all the way to somebody that's very tolerant of pests. And so they might enjoy one azalea. This is my favorite azalea on the whole property. Everything else I don't care about. So really all you're there is to look at are the azaleas, which may have lace bugs or something like that we know is going to be a stressor for the Formosa type of azalea. So that might become a key plant. Lots of trees are planted in memory of people, so they might have a key plant on their property that's like, well, we planted this tree for Uncle Jim that passed away a few years back, that sort of thing. So you need to not only what you think is important, but what the client thinks is important. So that would be the ones of particular interest to the client. And then we're going to develop sort of this action threshold. Once we know what is important to our clients and what's important to the landscape plants, and we're looking at them over time, we can develop this sort of action threshold. Again, if we have that client that doesn't want any pests out there, the action threshold might be every single visit you go out there, you are treating and monitoring. Whereas you might have a mite outbreak on a row of cypress trees, and you're okay with it until it gets to the point where my tree's now turning rust color at the beginning of August instead of in September like it should, because the erified mite population got out of hand. So I might be willing to tolerate it for most of the year, and then end of July, I know my action threshold is coming up, and so we do a treatment at the end of July, and then we could retain the foliage on those through the rest of the winter. The appropriate response process. So how do we want to respond? Here we set the trigger for when to respond. Now we're going to talk about what the appropriate measure is for getting it. So again, gather the information, assess the severity and implications of the problem, determine the client's expectations, and decide a course of action. Avoid the short-term treatment at the expense of long-term solutions. So if you're having to treat a plant every single year when the stressor may be an irrigation issue, go ahead and fix the immediate issue this year and get with the irrigation company to modify the irrigation so that we're changing the actual cause. We're not just treating the problem, but treating the cause of the problem. So you want these plant healthcare clients can be clients for decades. It's not like a removal where you're going in, you're taking the tree out and you never see them again. And you're going to see these clients over and over and over again. So you meet these client expectations and look for the long-term solutions over the short-term treatment. And every situation is going to be different. Every client is different. Every landscape is different. Even within the same landscape, you can have differences from front yards to backyards that can be quite significant. So here's our graphic for, we have our sign and symptoms might trigger some event. We have our clients, the plants, and the stresses are the big things here. So clients, perception, expectation, and confidence in the practitioner. In plant healthcare, many things that we do are not visible. So there has to be a level of trust that you are providing, in the example of a spray program, that you're providing the correct chemical, you're putting it down at the correct rate, you're doing it at the appropriate time of the year for that particular plant. And you're communicating that to the client as often and as thoroughly as possible. You have to set that expectation. It's not going to be 100% control. You can't have control over every little nuance to correct the problems. You need to express that to the client. You need to set the expectation that you're only going to come out 4 times a year because that's all they're willing to pay for. And so some things in between those 4 visits could get out of hand, but you need to tell them that's a possibility. So set that expectation. When it comes to perception, a lot of clients are perceiving that they're going to pay you and never have to do anything again. So you need to figure out what their initial perception is and compare that to where you need to set those perceptions appropriately. And then again, you have to have confidence that the practitioner is doing the right thing. So in our plant healthcare programs, after they purchase the program, we tell them what they're going to get. We tell them when they're going to get it. And then after the application, we circle back around. We made the application. This is the product that we use. These are the rates at which we used it, all that sort of thing. Did you have any comments? You're asking for feedback. You're making them part of the decision-making process, part of this response process. So by setting those expectations, you're going to have a lot less hassle. Another thing that can happen if you're not a great communicator is they're going to stop using you because they think that the problem's fixed. You go out there, you didn't set the expectation that this only works during the treatment period. You should have said, well, this is going to work for this year. They're going to be back next year. We'll have to treat again. We'll have to reset our action threshold or action response, something along those lines, so that you're letting them know they look healthy because you're doing your job. But if you're not doing your job, the same problems can return. So by doing that, you're going to build that confidence and use that confidence to your advantage. Again, we're going to talk about the plants and the stressors that they're under. You know, is it the right plants in the right places? If not, what are you going to have to do about it? What are these plants susceptible to? Are they susceptible to too much water? Are they susceptible to not enough water than what they're getting? And then again, here we have structural integrity. So again, plant healthcare is not all about chemical applications. It can also be about pruning. So the structural integrity of these plants, are they going to, you know, is the Japanese maple going to split apart? Is the elm tree going to split apart? We want to maintain health and structure as long as we can. So we might begin to recommend things like cable systems or propping systems, you know, a number of issues. So also we'll talk a little about risk, I think, next week, but this can also go into the risk category. Is this plant a risk? You know, if I have a tree that's growing a branch out and to the street, might be covering up a stop sign, that covering up that stop sign is an increased risk. So reducing the risk and keeping the plant healthy at the same time, we need to set those expectations. You can go ahead and prune that branch back so that it's not blocking the stop sign. So there's a number of reasons to prune. We're going to look at the stressors. You know, what's the diagnosis? What is the stress? So you're going to examine these plants. If they're not performing like they should be, we need to answer those questions. Why? What's the stressor here? Is it too much water? Not enough water? Is it not enough sunlight? Things like that. And what's the potential problem because of this stressor? Is it just not going to look good? Is it not going to be as green as the client's expecting? Is it going to have an impact on the tree structure? Is it having an impact on vitality? So these things are constantly interwoven. But at some point during this communication loop, you have to say, well, is intervention necessary? Have we reached the point where we need to make a chemical application, or have we reached the point where the tree needs to be pruned? So we're going to evaluate it extra close. We're going to see, okay, here's the sign, here's the symptom, here's maybe the causal event, communicate that back to the client. Having already set expectations, you're going to say, hey, we reached all these things that we were expecting to reach in order to make an application. So you're going to circle back around, make your application, and then the next time around, you're going to do the same thing. So every time you make an application in plant healthcare, you're also doing a monitoring. So you might go out, treat one particular plant, go back around, look at all the key plant material again to make sure that your program's on track. It's a fluid process. You don't just set it and forget about it. You're going to have to modify it over time because they're going to want more plants. They might want to take plants out, and they might put in more hardscape. They might put in low voltage lighting, which might cut roots. They might have to have, you know, things done out there that are going to impact the plant material. So be sure that over time you're incorporating these things into the plant healthcare program. So again, client education is absolutely essential. Tell them what products you're using, explain to them how they work, and they might not understand it, but they're going to appreciate it over time that you're letting them know what you're doing and why you're doing it. One of the big problems with clients is that they think that all aesthetic problems are health problems, and that's not necessarily true. So it might not look the greatest right now, but it might just be because of the time of the year, and it's not really a health problem. So these two don't have to be together. They can be separate things. In plant healthcare, we want to minimize the use of broad spectrum insecticide applications. Broad spectrum means that it kills a broad or a wide variety of pests. In plant healthcare and in pesticide application, you're going to hear the word pest a lot. Pest is the overall encompassing word for something that you don't want there. A weed can be a pest. A dog running the same dog path every day, compacting soils, can be a pest. A fungus can be a pest. So all of these things fall under the category of pest. So when you see pesticide, that's a really huge term. Instead, you could use things like insecticide, miticide, rodenticide, ovicides, bactericides. There's all these things that subunits that are more specific. So if we have just a mite problem, mites are not insects, so we would have to use a miticide. So we're going to use miticide to kill mites only so that we're not impacting the other beneficial insects that are out there. If you use this broad spectrum business, you're going to kill everything. You're going to kill all the beneficial insects, beneficial bacteria even that are helping the plant out. So you're going to kill all that so that you can have a pest resurgence or resistance. You can also have secondary pest outbreaks. So a resurgence mites are a pretty good example of what happens in resurgence. So you have a tree that every year you're getting the bad kind of mites, but wherever there's the bad kind of mites, you have good kind of mites, and the good mites like to feed on the bad ones. And as it so happens, as it turns out, the good mites reproduce a lot slower than the bad mites do. So the bad mites reproduce with an unbelievable speed. So if you're using these broad spectrum pesticides, you could kill off both the good ones and the bad ones, but which ones do you think come back faster? The bad ones. And so there's going to be some time elapsed between when you killed off all the good ones to when they build back up. So the bad ones can actually come back and just begin to do damage before there's even a population of the good ones. So that's pest resurgence. Secondary pest outbreaks, boxwoods are a pretty good example. We use that neonicotinoid that we talked about a little earlier. So we're putting that product down in the root system. It's systemic. It comes up and it kills the leaf miner as the leaf miner feeds on the spongy mesophyll of the leaf surface. But there's something else on the leaf surface that's not impacted by an insecticide, and that's going to be the mites. So because you kill, for some reason, when you kill off the leaf miners, you have a surge of mites. So that's a secondary outbreak. So you killed off one kind of pest, but it allowed another kind of pest just to take off. So that's a secondary outbreak. They're slightly different than a resurgence. So integrated pest management. Again, this is where plant healthcare came from. There's a lot of overlap between IPM and PHC. But IPM is the use of cultural, mechanical, biological, and chemical controls. There is still a threshold of treatment for a pest population, but here it's done based off a cost-benefit analysis as it pertains to crops. It's still going to minimize the adverse ecological impacts of intervention, except here it's more about how much it costs to do it. If I have 1,000 acres and I have 1 acre of that 1,000 acres that has some fungus in it, do I want to treat that 1 acre? Well, to gear up and treat that 1 acre is going to cost more than it is going to provide plants to sell at the end. It's going to offset the cost of having applied that fungicide. So I'm not going to treat it when it's 1 acre. Maybe I'll treat it when it's 10 acres big, because then I'll get more out of my crops than I would have if I just let it go. So there's a cost benefit analysis that has to be performed there as to when you want to take action. So your action threshold is a little different. But there's still your monitoring, you're setting up all these monitoring stations. So it's something that is very similar to plant healthcare. It's just IPM now is thought to have to do with money more than aesthetics. Injury tolerance can be influenced by the plant's phenology. So again, we're talking about some energy allocation here. It's the relationship between recurring biological events and weather changes. So it's going to spend a lot of energy making flowers in the spring. It's not going to spend energy making flowers in the fall because it doesn't make flowers in the fall. So you have this energy expense for reproduction in the spring. You have sort of this constant use of energy for secondary development. You have to expend some energy in the fall to take compounds out of the leaves and reabsorb them. So they do that at specific times of the year based on weather conditions and available sunlight, that sort of thing. And all of that, as it occurs over a cycle, because it's every year it goes through the same cycle, that's what is meant by phenology. So it's a recurring biological event. But we can also use these sort of ups and downs to talk about pest development. Most pests produce eggs. They don't have necessarily live birth. They make these eggs and they lay these eggs, and the larva can emerge from the eggs based on sunlight and temperature. And so we have this model called a growth degree day model. And if you go online and go to your area and look for things that happen on certain growth degree days, a growth degree day is sort of an accumulation of temperature over a long period. So it's the growth degree day model has to do with this sort of low growth threshold for plants, insects, and mites, and pests of the woody plants. There's really nothing's going to happen below 50 degrees. So the lower threshold and the daily average temperature, you're going to use those to continue to add. So it's sort of a complicated way of going around it, but every day you're gonna add today's degree day to yesterday's degree day. And so you could be in the thousands depending on where you are, you could be in the hundreds depending on the time of the year, or you could be at 0 if temperatures are below 50 degrees and we haven't gotten above an average of 50 degrees in this particular growing season yet. And you say, well, why do we need to know this stuff? Well, these pests, these eggs emerge on very predictable growth degree days. So you might have great fluctuations in weather. You know, Atlanta was a pretty tough place to use the growth degree. I mean, it was a great place to use the growth degree day model because it was so variable. You could have these really early summers, or you could have these really long springs. And so the growth degree day numbers could be tremendously different on the same physical date year to year. So if you're using this growth degree day model, you can start to say, well, we're getting close to the emergence day because it might happen on day 750. And so these things on day 750, sure enough, these larvae begin to hatch and start feeding on leaves or plant material or something like that. So you can use pesticides that last a very short period of time in the environment if your timing is really good. So you can use these growth degree day models so that you're getting it at exactly the emergence date, and you're going to wipe them all out in one application, and you're not going to have to start treating too early or treat after it's treatable. So that's the growth degree day models come in very handy. Monitoring stations are hard to come by. UGA does maintain a few growth degree day calendars in Georgia, but last time I checked, we really didn't have any that were in metro Atlanta area that you could use. Some plant healthcare companies, that's all they do. They might maintain their own growth degree day calendar for their service area. So as you can imagine, Atlanta is going to be different than Cleveland, Georgia. So they're going to have two different, even though it's the same state, they're going to be on different growth degree days. So management options, focus on prevention strategies and pest avoidance. So if you're planting plants that are resistant to, say, fire blight, then you're not going to have to treat for fire blight because it's a resistant plant. So when you're designing your landscape, include these things in the design. That way you're not going to have to use as many pesticides. Suppress pest populations to reduce the level to tolerable levels. So most pesticides, the labeling will have a range for the rate. So it goes from either a low rate to a high rate. Here, again, I'm treating oak wilt here, and there is a low rate that's used preventatively, and then a high rate that's used if the tree's already infected. And the difference is 100%. So I might use 5 milliliters per inch of diameter for the low, and it'd be 10 milliliters for the inch of diameter if it's already infected. So it doubles the amount of product that I have to use. So if I catch it early, I'm using a much lower level than I would have to. Remove and replace with resistant varieties. Again, if you love crab apples and you're losing your crab apples, or you're losing your dogwoods, which is happening all over the country, you might replace your Cornus florida with one of the Korean varieties. So you're bringing in something that's more resistant to that Discula leaf spot. Or with the crab apple, they have crab apples that are highly resistant now to fire blight. So you take out those old ones and replant with the newer ones. Good sanitization. If you get infected plants, something like boxwoods, this boxwood blight that is around, it really hasn't gone totally destructive yet. That's an example of when good sanitation is needed, because it gets into the soil. So you'd have to not only remove the plant, but remove the soil associated with the plant, remove some extra soil even outside of that, just to be sure before you plant anything back in the exact same spot. That rosette disease on roses, same kind of thing. You got to pull it out, get some of the soil, get the roots out, and come back with something different. Don't even come back with roses, because whatever you come back with is just going to get it again if it's in that family. Another thing that you can do is avoid overhead irrigation. The longer the leaves stay wet, the greater the likelihood that you're going to develop a fungal problem. And remember, fungal problems are by far and away our biggest pestilence in our landscapes. So try to cut back on this overhead irrigation, especially in the woody plant material. There's all kinds of really cool irrigation stuff out there now that's available. So do some research, figure out what's might be the best. Work with your local irrigation guy. If you don't do irrigation in-house, work with one of these irrigation specialists to try to keep the foliage dry as much as possible. You want to do proper mulching. Mulching is one of these things that there's a certain amount that's ideal. If you don't have enough of it, it doesn't do its job. And if you have too much of it, it can hurt the tree if you do too much. You've all seen these sort of volcano mulches. You definitely want to avoid that, because you're running it up the trunk of the tree, you're keeping it moist, and it's so thick that you're having degradation in the mulch itself, which produces heat. And so you're making a hot, damp, dark place, which is what sounds like a great place to grow a fungus, doesn't it? So you don't want it that thick, 3 to 4 inches thick. And you also want to use aged mulch, so that it's already gone through that denitrification process where it's burned off the bacteria and everything that was in it. So you're putting the right kind of mulch down, you're putting it down at the appropriate thickness. Supplemental watering. Do you need to irrigate all the time, or just irrigate some of the time? Or maybe it's even more simple than that. Maybe it's just hand watering one particular plant a couple times a week. Just, keep in mind, these are all management options. And another thing you want to do is avoid monocultures. Most of the tree ordinances now dictate that you have to have a certain diversity of tree species in the given landscape. Might be 10% oaks, 10% maples, blah, blah, blah. Some of these ordinances are really unwieldy and get very specific about it. But the reason that they're doing it is, just think if you had all elm trees and all of a sudden you get a disease that wipes out elm trees, then if that's all you planted on your property, boom, you've got a big issue. That's where our chestnut trees went. We planted all these chestnut trees along the streets. They were great trees. They were huge. Everybody loved them. They were also native. They were out in the woods. And then suddenly we get this blight that kills them before they have a chance to get into the reproductive cycle. And so now we've lost nearly all of them. So avoid monocultures if at all possible. We also have some other controls mechanisms here. We have, biological controls, chemical controls. We've sort of focused on the chemical control, the spray applications, and we've talked about the cultural control, planting the right trees in the right place, that sort of thing. Physical and mechanical control. If you have bagworms, you can go out there and pick them off and throw them in a bucket of soapy water or something. That's physically changing it. Another physical or mechanical control, could be pruning, things like that. biological control, you might introduce insects into the beneficial insects into an environment that can help control the bad pests in your area. And then there's also legal control. This might show up in the form of a tree ordinance, where you have to have that diversity in your landscape, or you might have to apply for removal permits above or below certain diameters of trunk. So all these things play together and should be part of your management, your designed plant health care program. So these biological controls, you can either conserve or augment the beneficial insects to decrease the pathogen. And there's a few drawbacks to it. It can take days or weeks to work if it works at all. There's three main types of natural enemies. There's predators, parasites, and pathogens. So you can introduce a predator like ladybugs. You can also have one like our praying mantis over here. This is a predator. You can have parasites. There are these. Most wasps are very, very small. They're like the size of mosquitoes or smaller, and they like to lay their eggs in living things. And so they'll go and deposit eggs in one of the bad guys, in one of the caterpillars maybe, and it kills the caterpillar. So that's a beneficial parasite. You can also have pathogens out there. You can actually give these things a disease, and there is another one on here that's growth regulators, but we'll talk about that, I guess, under a different topic. But a good example of this was up in North Georgia and then the Carolinas. They had the hemlock woolly adelgid, which is that little fluffy white kind of cute looking thing that gets out there and kills off these hemlocks. But ladybugs kind of like to munch on them. So the U.S. or the Georgia Forestry Commission in the conjunction with the U.S. Forestry Department paid to go and release these things by the hundreds of thousands in North Georgia to try to protect our North Georgia hemlock trees. Well, they went back in this days to week period here to see how it was working, and they couldn't find a single ladybug. And because these were introduced, they were a very specific variety. And there was a forester in northern Alabama that says, "Hey, I think I found your ladybugs." So they wound up migrating from North Georgia to northern Alabama. So there's no guarantee that these predators that you bring in or parasites that you might bring in, there's no guarantee they're going to stay where you put them. That's another sort of drawback to them. Mechanical controls, again, this is like you can pick them off. If you have bagworms, you can pull off the bags. If you have tent caterpillars, you can take a stick and tear it up. You can put on physical barriers, like some caterpillars crawl along the ground, go up the trunk of the tree, out and feed on the leaves. So they make this sort of, there's one product called Tanglefoot, and I don't recommend one over another. It's just the one that comes to mind at the moment, but it does what it says it does. So as the caterpillar's crawling up and gets into this mesh of fibrous webbing, its feet get all tangled up in it, and it gets caught there, and it never makes it into the canopy. So that's a physical barrier. Pruning, fire blight typically initiates out in the tips of the branches. It can initiate where there's flowers. So if the tip has a canker on it, an overwintering canker on it, you can prune a couple of feet back behind it, and you can prune off that pathogen. So those are three of the mechanical ways to go. So now we'll talk about these chemical controls a little more. We have fungicides. These are usually applied as a protectant. Fungicides don't work all too well. Well, there is no cure, put it that way. So if it's like the oak wilt, once the tree has oak wilt, it's always going to have it. So you have to retreat these trees every year to keep the level of alamo in the tree high enough that it keeps the fungus at bay. So it allows for clear vascular tissue the following year, but you're going to have to continue to do it. However, if you use it as a protectant, you might only have to use it for a few years as it travels past your area in the root system. So much better to use it as a protectant. Insecticides come in a couple of varieties or a couple of classes. We have contact pesticides. Contact means the pesticide has to touch it, has to come in physical contact with the pest. lace bugs on azaleas, the lace bug feeds on the bottom side of the leaf. So if you're spraying on top, you're not going to kill all of them on the bottom side of the leaf. So you'd have to use some extra pressure and set your rig to fog, and then you're swirling it like this so the branches are moving around, and you coat both sides of the leaf because you have to come into contact with it, contact herbicide. Your other option is a systemic pesticide. Systemic means that you can get it into the vascular tissue and translocate it out into the roots, stems, and flowers and leaves. This is a very effective way because you're not having to get both sides of the leaf. It's pretty quick to apply systemic pesticides. They can be fairly target specific. So, and there's getting to be more and more of these available to us every year. What's not readily available in systemic format are fungicides. We are just now beginning to get a few systemic fungicides on our market that are effective for our diseases. So just sort of keep that in mind. Yeah, so I would be remiss if I didn't tell you that read and follow all the labels on your products when you use them. Labeling is not just what's actually printed on the container. So you have to have the complete labeling. When I purchase a product, and it's the first time I purchase a product, the first thing I do is I get all the MSDS sheets, the material safety data sheets that go with the product that describe the product. It has all the correct numbers on there that identify the product that you're using. And then I go to the manufacturer's website, and at the manufacturer's website, they will have the complete labeling. So there might be more labeling than what's printed on the bottle. And that's going to show up in the complete label from the manufacturer. Occasionally, you might even have to go to your state. Here in Texas, the broadleaf herbicides are highly regulated compared to other parts of the country. So, and it drills down county by county. So you might be able to use 2,4-D in my county, but not use it in the adjacent county, something like that. So where you can use it is also in the labeling. So like if you look at these things, they'll often say California and New York have additional restrictions. Please check with your state. Or you might say have one that's like in Texas, please check with your county. So all of those things combined produce the complete labeling for the product. So make sure that you've read through that and that you understand that. Also, anybody that uses the product needs to be able to read and understand that complete labeling. Because remember, you're going to become liable. You have applied pesticides, you've applied chemicals somewhere that has the ability to kill things. So that puts a lot on your shoulders. So the more you cover yourself by reading and understanding and using them properly, the better off you're going to be. Again, these pesticides also include miticides, bactericides, and herbicides. To learn more about these, go to your state is going to have a commercial pesticide license. They're going to have both an applicator's license and a contractor's license. And you have to have both of those things on your payroll in order to charge for their application. So if you're applying, even if you're just spot spraying Roundup for a client, like you cut a stump down and you spray the stump with Roundup to keep it from coming back, if you don't have a licensed applicator on staff and your company does not have a pesticide contractor's license, you can be held liable for that application because that's illegal. Yeah, so again, pest resurgence, this is what occurs or may occur when the bad guy rapidly rebounds in the absence of natural controls. Typically, this happens when you're using a broad spectrum insecticide. Secondary pest outbreaks, these may occur. It takes advantage from the lack of competition. So even though, we talked about pest resurgence being in the mite population because there's good mites and bad mites. Secondary pest outbreak means that there's a totally different kind of pest that's going to take advantage because the other pest isn't there anymore. So that would be a secondary outbreak. Fungi have the ability to adapt to fungicides fairly rapidly. And because of that, they build up what we call a pesticide resistance. I can go out in my yard right now and spray nutsedge with Roundup, and my nutsedge pretty much says, ha ha ha, that's pretty tasty. Why don't you give me some more? So it has developed a resistance to glyphosate. But more commonly, you're going to find this resistance build up in fungicides. And because of that, you're going to want to rotate classes, or the MOA, the mode of action. So every year, I'm going to use this class this year, this class next year, this class the following year, and then start back over with whatever class I had the first year. And that's going to, it won't be able to adapt so fast that way. In all likelihood, it shouldn't adapt at all if you're changing them out on that regular of a basis. Are there alternatives to pesticides? Well, sure. There's some biorational control products, such as insecticidal soaps and horticultural oils. So these things are best used, and both of these are best used in the early stages of a problem. So the crawler stage of scale. So scale insects makes a covering on the outside of itself that's very resistant to the direct application of an insecticide. But when the eggs hatch, they come out from underneath that shell and try to get out onto the fleshy green new twig growth before they start feeding. So when they're in that phase, they're very susceptible to something as simple as soap. Insecticidal soap breaks down the surface tension on the exoskeleton of the insect or the mite, and as it encapsulates it, it suffocates to death. So, but that's only when they're very, very small. The bigger they get, the less effective insecticidal soap becomes. Insecticidal soap breaks down rapidly in the environment. It's non-hazardous. Insecticidal soaps now don't even contain phosphate, so you're not going to be contributing any phosphates to the soil either. In a similar fashion, horticultural oils work. The drawback to horticultural oils is that you need to make sure that you're following the labels, again, very specifically for your specific area. These oils are often referred to as summer oils or dormant oils. It's really the same oil, just a different concentration. And so they may say summer oil, and in your head you think, okay, this is what I can use in the summer. Well, here in the South, quite frequently our summers get well over 80 degrees, 90 degrees, into the hundreds. At those temperatures, you shouldn't be using horticultural oil at all. So if you read the label, it'll say do not apply when temperatures are above or expected to be above blah, blah, blah. And dormant oils, their complete labeling says you don't really use them when it's freezing outside. Again, not a huge issue in the deep South. We could apply these at the high rate most of the dormant season. And again, it does sort of the same thing here. It suffocates the insect by encapsulating its body in this oil that it can't get out of. And even the eggs, so if it gets around the outside of the egg, eggs still have to respire. Remember, we talked about respiration. So the egg has to be able to absorb oxygen and give off carbon dioxide to keep it going. So if you coat it in this oil, it can't exchange with the atmosphere, and it kills the egg. Again, the drawback to the summer oils is this phytotoxic injury. If it's applied, if it's too dry outside, then it's too hot outside. When you apply this stuff, it acts like a magnifier, and you can scorch the leaves off. You can burn the leaves right off of the plant. And remember, we had those sort of secondary buds and even tertiary buds. So if you use the horticultural oil on a hot enough, dry enough day, it'll even smoke off those secondary buds. So be careful there. We have botanical pesticides, neem, pyrethrins, rotinones. We talked about these already. Nicotine, neonicotinoids. And then I alluded to these growth regulators a little earlier. These are pretty effective. What they've discovered is that there is a chemical that is produced by, or a gene that is turned on by an insect that produces a certain chemical that allows its skeleton to get really soft. And as it gets soft, it can grow a little bit and bust out of it. You've seen those cicada shells on the side of trees or houses or whatever. So that cicada had to produce a substance to soften that exoskeleton up so that it could escape and fly off. Well, there are products out there that if you're treating the the insect with it in one stage, it inhibits its ability to manufacture that softening agent. And so it continues to grow on the outside as if it's going to bust out, but it can't bust out. So it literally grows itself to death and kills itself inside of its own shell. It's kind of gross. There's also trapping, monitoring stations. The regulators can create sterility so that it can't reproduce. There are microbial pesticides. We talked about being able to give it a disease. So Bacillus thuringiensis is an example of that. So there we go. So that's the plant healthcare section. Have we got more questions?
We do. So Joe had said, save this for the end. He said, back to cabling. What are some typical situations where cabling might be warranted? At what point does the expense nullify the need for cabling?
That's really a great question. And it can be a difficult one to answer. If a tree, and we talked a little about liability, so I'll talk a little deeper here about liability. If a tree is in a situation where it's hazardous, like you have a branch, it's actively failing, or the trunk that's actively splitting apart. If it's actively doing that, and you can describe the tree as a hazard by installing the cabling system, the purpose is that you want to keep it together, but it's not going to change the liability. It's always going to be a hazard because it was defined as a hazard. Cabling and bracing doesn't change that. So if it's at that point where it's high risk and there is a target, because remember, hazards or high risk hazards have to include a significant target. So if it's a tree out in the front yard, nothing else around it, there's no kids that's playing there, fine, go ahead, cable and brace it, because the client feels like that the likelihood it's going to hit something is fairly low. You, as the person who's putting it on, also feels like it's pretty low. So in a case like that, it could be warranted, but don't sell it as if you're going to reduce the hazard. If it's already been declared a hazard, it's a hazard. Whether you install it or not, it's still going to be declared or still have a state of hazard because it has a significant target. So then the cost benefit comes from, typically would be a much smaller tree like Japanese maples or young maples, where you can pull it back together. It's going to look fine. It's going to live for decades and decades. So in those situations, it's usually warranted because the client doesn't want to rip it out and start over again. So if you have, a $6,000 Japanese maple that you can spend $300 on to keep it from falling apart, again, it's not a hazard, but you can pull that tree back and keep it, then it would be warranted in a situation like that. But it takes a lot of feedback with the owner. Most of the tree care companies that I work with coaching and that sort of thing, they prefer not to install cables at all. And if they do, they're installing these more dynamic cable systems now. But it's really based on interaction between the arborist and the homeowner, setting the expectations, feeding them, let them always decide if it's worth it or not. I learned very early in my career that, $100 to me is a big deal. $100 to some of my clients is, the 5-year-old's daily allowance. It's all over the place. So that's why it has to be an interactive process. Is that the question he was asking, do you think, or was there?
I believe so. Let me know, Joe, if anything else comes up and you need clarification. So far, I haven't received anything else in the Q&A. So I'll give y'all just a minute to think and see if you need any clarification on that last question. For everybody who is here today needing CEUs, of course, I have already dropped that sign-in sheet in the chat. So if y'all can make sure to fill that out, that would be helpful. I see some already rolling in. Christopher, Jeffrey, I've already got yours. Any other questions for Rob today before we send him on to carry about his day? Doesn't look like I got anything for you, Rob.
Just, my recommendation, I always, these classes are meant to sort of help you to understand things that you've already read. So make sure that you're reading the material before you sit in on these, because these are really meant to help you clarify ideas and not necessarily be the sole instrument for education. And in addition to this class and to your study guide, I also highly recommend getting that set of ANSI standards and reading through those ANSI standards, because they're going to be a lot more inclusive and precise. It's always better to go into a situation with too much information than not enough, is the way I look at these. So between a little mentorship and reading before you come and getting these other things, I think you'll get a lot out of the class.